Okay, sorry, I hope you guys can hear me now. So you can see the recommended books, Oppenheim and Wilsky, second system, second edition, or any book after that, third edition, fourth edition. I believe fourth or fifth edition is already out. You can use any book. I've already uploaded the soft copy of this book along with all 19 slides that we will cover throughout this course on the file section of Teams. So you can just download it from there. I've also uploaded recommended or helping MATLAB text. You can use that or use whatever you feel comfortable with. I believe all of you already know MATLAB, so you will not face difficulty in the labs. There are other recommended books, Signal System by Haken. There are multiple different websites. Some of them are mentioned here. This course, Signal System, is taught all over the world. Anybody taking engineering, cover this course, Signal System. It's a core course, and we don't call a person an engineer if he does not know signals and system. So you can go to any website, MIT courseware, Stanford courseware, YouTube, whatever videos you feel comfortable with, you can download. The course content and syllabus remains the same all over the world, so there's no difference. And some of these slides that we will be covering here are taken from different websites also, so you can see those slides being used by multiple different teachers in different universities. This course is about signals and systems. We'll cover very basic things in the first 1 or 2 weeks about what is a signal, what is a system, properties of signals, properties of systems, and initial about 1 to 2 weeks will be very kiddish stuff, about fourth, fifth grader stuff. So you'll not face any difficulty there. But later on, we'll just start picking up and start talking in detail about other concepts. So as I mentioned, the syllabus remains the same wherever you cover this course anywhere in the world. It's a very well-known course. We start with concepts about signals and systems. We talk about mathematical models. We talk about continuous time system, discrete time systems, energy power systems, linear system, and multiple different basic concepts we will cover. The first topic that formally, you can say, starts the course is about a linear system and convolution. Convolution will be the first theory we cover, and then we build upon that theory. And in that, we'll talk about impulse responses, input as continuum of impulses, and multiple different things related to convolution in continuous time and discrete time. We'll talk about some basis functions. Basis is an English word. It is basically building block, a simple building block functions, very simple functions. And we will see that how that basis functions or simple functions can be used to build up more complex functions. Now, functions or signals is one and the same thing. And once we cover this course, you will come to know about terminology. Some of this terminology right now may seem very complex, like mathematical model, very high sounding. But once we go into it, you will see it's very simple stuff. So we'll talk about Fourier transforms, Fourier series, sampling of discrete time systems, Laplace transforms, and transfer functions for continuous time systems, transfer function for discrete time systems. They are basically Laplace and Z transforms. So many of these things you may have already heard about, like Fourier transform, Fourier series, Laplace transform, Z transform. You may have covered it in mathematics. So these terminologies may not sound very unfamiliar to you, but here in this course, we'll be practically using them. It will not be a mathematical approach where you need to remember a few formulas and just work with about 2 or 3 pages of solutions. It will be just that what these functions are, where are they used, so why do we study, why our life was made miserable by mathematicians, so why all these basics were taught to us. So we'll see in this course. This is an old slide. I always show it to all the people taking this course, but in this particular semester, quizzes will not be taken as per the policy. Instead of having 2 sessionals, you are going to have 1 midterm. So the numbers of quizzes will go towards the final. So final will be something like 60%, and sessional will be something like about 40%. And I will see if assignments have to be graded or not. and accordingly assignments may carry 10% marks. If they carry 10% marks, then final will be 50. Then it will be 10, 40 and 50. So right now I've not made up my mind right now, but one thing is for sure that your midterm will be 40% and your end term will be either 50 or 60%. Assignments may or may not be graded. If graded, it will be 10%. So right now the policy about assignment is also not very clear, that how many assignments we can give, whether we can grade them or not. So let me find that out, and then accordingly your percentages will be adjusted. So let's just quickly have some very basic introduction. So first week, first about 3 hours that we cover, half an hour we have already lost, so 2.5 hours that we cover. It will be very, very condition basic stuff, as I mentioned. So we start with a very basic question, that what is a signal? A very common sense question. And let me assure you, I'm not going to ask you that type of questions in your exams, that what is a signal, and you are expected to just give me a Xerox copy or photocopy of whatever is written. So I'm not going to ask that type of things. This is more of a conceptual type of course. Just understand what the thing is, and you'll be tested about the understanding part. But still, for the sake of it, let's go into it. What's a signal? A signal is a pattern of variation of some form. So if there is a quantity which is changing with time, we call it a signal. So you can define signal with whatever words you feel like, but everybody know what's a signal. So examples of signal are, in electrical signal we have voltage and currents. So these are things which carry some sort of information. So sound intensity is a signal, image pixel intensity is a signal. So there are multiple different types of things. In electrical, voltage, current. In acoustics we have acoustic pressure or sound pressure, and in mechanical it can be velocity, distance traveled, things like that. In video, multiple different types. So signal can be any signal. This course is not only taught to electrical or computer engineers. This course is taken by all the engineers, whether he's a mechanical engineer, is becoming a mechanical engineer, or mechatronics engineer, whatever. So that is why in this course we don't limit ourselves to any one particular type of signal. So it can be any signal. So what we study here is that what are the properties of signal, how do we represent a signal, what is a continuous time signal, what is a discrete time signal. So some common types of groups of signals. So we'll talk about that. We will not limit to any particular category of signals. So as I mentioned, the next question that comes up is that if we know what's a signal, then how do we represent a signal? Now, mathematicians typically write an equation or function to represent a signal, and that has got some sort of a independent variable. So it can be, let's say, variation of temperature of this room over the day. So we can write an equation for that also. So mathematicians tend to write an equation to define a system. But we engineers typically like to graphically represent a signal. Along with using the equation, we also love to physically see that how that signal is varying. An example of that, you can see the figure or graph shown here. So we have some signal which is function of time. By function of time, it means that it is changing with time. So y-axis is the value and x-axis is the independent variable time. Almost throughout this course, for continuous time signal, the independent variable will be time. So it is time on x-axis, and on y-axis it is value of that signal. Now this signal, which is a function of time or which is changing with time, can be any signal. It can be voltage, it can be temperature, it can be, I don't know, velocity, sound intensity, whatever. So we can just plot it and it will look something like that. Okay. This again, very intimidating, especially for non-electrical engineers. But again, this is just for reference. You are seeing a simple figure where a resistor capacitor is joined with a voltage source. So you have already taken electrical basic course, electric circuit course. So you know what's a resistor, what's a capacitor, and what's a voltage source. So in this diagram, signal can be anything. It can be current, can be a signal. Voltage across capacitor can be a signal. So we can have multiple different types of signals that we can pick up and plot. It can be voltage across resistor. So multiple different signals can be taken up from here and plotted. Now, if you want to write an equation for that signal, for example, if you want to write equation for current. So current across a capacitor is voltage drop across a capacitor divided by resistance. So Vs minus Vc over R. So we are using that T inside showing that it is changing with time. So it is just Vs minus Vc, which is voltage drop across the resistor divided by R. That is going to give you current, IT. Next, we know the current is flowing through a capacitor, and the very property of capacitor is that the current and voltage across a capacitor are linked by the equation shown that I is equal to C times dV by dt. So current flowing through a capacitor is linked with voltage across a capacitor by this equation. This again you may have already seen. And if we just plug in the second equation, the first one, we end up getting the third equation, which looks again very intimidating. So this equation, the third one that we see, actually has got differentiation inside. So what type of equation is this? What do we call that equation? It's a first order differential equation. So this first order differential equation is very interesting equation, and later on we're going to see. You studied differential equation also in mathematics. You studied complex numbers also in mathematics. You studied Fourier transform, Laplace transform in mathematics. And many of you may be wondering that why we are studying it. What's the use? What is this calculation and computation, and why our life is being made miserable by these pages and pages of calculations? So in this course, you will start finding out that why all that mathematics was given to you. And you will not be using that complex mathematics. It was just to sort of train you. But in this course, you will see that where those mathematics is actually used. So the third equation you see is a very interesting equation. And if we see the blocks that we have already drawn with the voltage source and capacitor, if we consider Vs as input voltage and Vc as the output voltage, then this whole electric circuit can be thought of as a system which takes some input and gives you an output. So input is Vs, source voltage, and output is voltage across a capacitor. And inside that system, we have this combination of resistor or whatever. And the equation, the third equation that you see, is giving you relation between input and output. Input Vs and output Vc. But that relationship ends up having a differential in between. I will come back to this equation again, and you will see that why we write such equations and what these equations mean. Now in your labs, you are already covering this MATLAB. A part of MATLAB is Simulink. I hope you know Simulink. So Simulink is a very simple software where you can do modeling simulation type of thing. So this circuit that you see in Simulink, we can just drag and drop and attach these things together, and then we can just see that how Vc is changing and how Vs is changing, or how if we change Vs, how Vc changes. And the output that you get from Simulink is this figure that you see down below. That the yellow line is basically Vs. If you change Vs, we see that how Vc, which is your purple line, that how that Vc changes. So Simulink, very useful piece of software, and in your labs you will be covering that. So we see that if we give a particular input Vs, the output Vc changes. And how it changes, we have an equation which gives us relation between Vc and Vs. We have MATLAB and Simulink where we can just patch all these things together and see that how changing one changes the other. So these types of things you will see in this course, especially in the lab. So coming back to the basics again, we talked about signal. Now there are basically, if you just categorize, there are basically two main categories of signal. One is a continuous time signal. Example of a continuous time signal you can see in the slide. So it is a continuously varying line, and with time the value of that signal is changing. So we draw a continuous time signal like this. This is how a continuous time signal looks like, and this is how we represent it. And typical independent variable is time because this function changes with time. Now, What we can do is the figure which is on the lower half. What we can do is we can just take values at equal amount of distance. We can just take values. These green lines are basically vertical lines where we are taking values at small intervals, equally spaced interval of time. We can pick up values for this continuous time signal. So once we have picked up these values, then what we can do is we can plot those values separately. Here you can see that dotted line is your original continuous time, and the red line is basically the values that we have picked up. The dots actually gives you the value, and the straight line which joins with the x-axis, this shows you that at what time instant that thing was taken. Now, this is basically a discrete time signal. The second graph that you see where we have just done away with the dotted line. The second graph you see is basically a discrete time signal. So why this is a discrete time signal and what is a discrete time signal? In discrete time, it's an English word discrete. Instead of a continuous, it is having values at discrete interval of time, at specific interval of time. Discrete means specific. So we are not having values at all intervals of time. It's not a continuous thing. We are having values only at a particular instance of time or at discrete instants. So this type of signal is discrete signals, where we don't have values at all time intervals. We have values only at specific time points only. So discrete time signal, we plot it like you see here. This type of plot, again, you know MATLAB. What type of plot is this? What do we call this graph? No, the representation. It's not a bar graph. It's a stem plot. So in MATLAB, we have command if you just want to plot this continuous type of thing. It's a plot command where you end up getting a straight line. And if you have specific values that you want to draw on graph like this is a stem plot. So discrete time signals are represented using a stem plot. So in MATLAB, you will just cover that. If you already know, you can just practice it yourself. So this is how we actually represent a discrete time signal, where the values are graphically shown using a stem plot. Now we saw two broad categories. One was continuous time signal, the other was a discrete time signal. Now the question arises that, well, we know continuous time signal and we have seen that we can extract discrete time signal from continuous time signal. The question arises that why we convert a continuous time signal into a discrete time signal. First question. The second is that if we have to convert in discrete time, how do we convert a continuous time to discrete time? Although looking at this, it looks very simple. We just take values equally spaced. But how close space should be these samples? Because if you see the value top graph, if you see the values second and third, in between there is a peak. But that information is lost once we convert the continuous time to discrete time. That peak cannot be seen. So how do we ensure that this peak is also seen in discrete time? How do we ensure this? That once we convert into discrete time and draw a stem plot of discrete time, we should be able to see that small variation and small peaks also. So what can we do? Come on guys, it's just not a very rocket science. Just we can just have closely spaced samples. So time interval can be reduced. So we can have large number of samples taken in the same time interval. That way, all the variations will be picked up. Is that right? So for example, if the time interval in between was 0.1 second and we were taking, let's say, 10-second data, that means 100 points. Theoretically, yes, if we decrease the time interval to negligible or zero, it becomes continuous. But that is exactly the question which was being asked here. Once we convert into discrete time, a continuous time signal to discrete time, then how close these values should be? What should be the time interval selected? Should it be 0.1 second? Should it be 0.01 second? Or should we just visually see? Okay, here it looks like 0.01 is fine. Should we visually see each time? Now, visually seeing it each time and then selecting time interval doesn't make any sense. It has to have some method by which we just can use a particular time interval for any given signals. So this is what we are going to see in this course, that once we have to convert a continuous time into discrete time, what time interval is optimal? Now, the question here is that, well, select the smallest interval possible, select 0.001 second. It should cover most of the signals. Why not select the smallest one? The problem with selecting a very small time interval is, as I was mentioning, if time interval was 0.1 second, for 10-second data, how many values? 100. So 100 data values, 100 points. So if those 100 values are written down or stored in computer, if each value is taking 1 byte, 8 bits or 1 byte, right? So 100 values will be taking how much? 100 bytes. Now, instead of 0.1 second, if we select 0.01 second, now the same 10-second information now requires 10 times more, 1000. If you select I don't know, 10 zeros, that means 10 raised to the power of 10, that additional amount of storage is required. So it will be wastage of resource. So it has to be some optimal value that, okay, if we select this much, it is optimal, it will cover everything. We don't need to select an interval lower than that. So a very small time interval ends up wasting resource because the same amount or same time duration will require much larger number of samples. Okay. Now I am using the word discrete time, but you are all digital age people. So any idea? This youngsters doesn't feel good. You have heard about digital signal. So I'm talking about discrete signal. So this signal that you see, the lower one, is it a digital signal or a discrete signal? So what is a digital signal then? High-low. That means ones and zeros. So this one is not ones and zeros, this cannot be digital, this is discrete. Right? So is that right? Anybody who wants to further explain this? The distinction between discrete and digital. Come on, all of you are from digital age. So we have all the digital circuitry and everything is being converted into digital. So what's the difference between discrete and digital?
Typically, we have only two values, 1 and 0. And in discrete, you can have
two values. This first continuous time signal, if you want to convert it into a digital signal.
So all the crush will be 1 and all the crushes will be 0.
But can we capture this signal then? Then we store this signal. So that means this signal cannot be stored as digital. Is that right? No, it's not right. So let me give you the difference, a very small difference. You see, this thing is right that the lower graph that you see is basically a discrete time signal, because these values, these red dots that you get, these values will be something like 2.185, then 3.2345, then 4 point something. So decimal values. And these decimal values, we can write it on a piece of paper, we can store it on a computer, on a hard drive, whatever. So we have converted that signal into discrete time. These values are decimal values. This is a discrete time. But what's a digital then? The difference between digital and discrete is very, very small difference. It is just that these values are represented in binary. If you represent these numbers not in decimal number, in binary number, we know that we can represent any value in binary number. Is that right? And again, choice is ours that once we want to convert any decimal number into binary number, how many bits do we use? Do we use 8-bit, which is 1 byte? Do we use 16-bit? Do we use 32-bit? Right? But once we convert from decimal value to this binary value and then store, then that signal is known as a digital signal. So effectively, there is no difference. The difference is only in representation part, that instead of representing the value in decimal, which is for discrete time, if we represent it in binary number, then it becomes a digital signal. And we can convert any continuous time signal into a digital signal. It's a two-step process. First, we pick up the values, decimal value, then we convert it into your digital signal. Now, in each step, we end up losing some information, or as we say, distorting the signal. Because as you see here, whatever we do, if the signal is very fast varying signal, even if you select a very short time duration, it is very likely that you will still miss out some peaks or some variations. So slight, you can say, loss of information will be there once we convert from continuous into discrete. There is another loss of information once we convert discrete into digital. And why is that? It is just changing binary decimal number into binary number. So where is that loss? So as I mentioned, first value can be 2.1837 something, second value can be 3.438. But once we are converting into digital, so I don't know whether you are giving me the same answer which I wanted, but let me elaborate it. The problem is that that number 2.18 something something something, if we want to convert it into a binary number, if you have just 8 bits, the closest we can come will be something like 2.25. 2 and then 2.25. In between 2.18 something, that we cannot have. So the value will not be exactly same value, it will be slight variation. Now, how do we fix that? As in the first step, the fixing part was reducing the time interval to capture all the variation. The second part, converting into the digital one, it is to increase the number of bits. So if we have 16 bit, then 2.125 is closer than 2.25. So we have lesser, you can say, loss. If you go for 32 bit, even more closer. If you go for 64 bit, almost exact, very negligible loss. But problem again, instead of 8 bits, if you are using, let's say, 1 to 8 bits, you are wasting resources, you are wasting memories. So it is a give and take. It's sort of a compromise. And this compromise, you as computer engineers should know that once we are converting from continuous time to digital signal, there will always be a compromise. If you want very high quality, very exact reproduction, then the compromises are the sampling rate or number of samples have to be increased, so more storage. The digit representation, you need larger number of bits. Instead of 8, go for 16 or 32 again. So whatever you do, it's a compromise. You still end up losing something, but amount of loss, how much amount of loss is acceptable? That you as engineer have to judge. Well, for 8 bit, we are having, let's say, loss of information, which is 8%, 10%, less than 10%. But we want less than 1%. With 16 bit, yes, we are having close to 1%. So it is acceptable. We don't need to go for 32 bit, because with 32 bit, maybe 0.8% loss, we don't need to go that low. So it's a compromise. So we just select that type of thing. So that actually gives answer to few questions here, that how do we discretize and distinction between discrete and digital. But, and how to denote discrete signal, we also covered that. The first question still remains, why do we need to convert any continuous time into digital signal? Why? Why do you think?
Processing.
Okay, processing. Anything else? You see, most of the signals we come across in real world, it is continuous in nature, like audio, like whatever voltage, currents, they are continuous in nature. We humans have learned that these continuous time signals, using some basic techniques, we can convert it into digital signal, and then we can store it on computers and all that. But why? Why do we do that? What advantage do we get? Okay, we have personal computers which have processors which can work with digital data. Yes, we can do processing. But if you just need to store, for example, I'm just speaking here and somebody wants to record it. Huh?
So even for storage, you need to digitalize it.
But we can have that magnetic storage, analog storage. You see, once I was young, again, this example I gave in the last class and I give in every class, let me give it here also. Once I was young, the audio used to be on C60 and C90 cassette. I don't know if we still have it or not. I don't know whether you guys still use it or what. So the latest gadget that came once we were young in your age was Walkman, where we used to plug in that thing. And it used to have just 60 minutes of audio songs. And to get a high quality song recorded, I come from Lahore. There was a shop by the name of Bomb Beat, very in thing in that days. So they used to charge hell out of money. In those days, 100 rupees was something like 10,000 now. So 100 rupees recording for one cassette. And anybody who got a cassette from Bomb Beat recorded used to just flash it with a sticker Bomb Beat. So high quality audio. Walkman we're listening. Now you guys have this small USBs and MP3 players, and instead of 1 hour, you have, I don't know, 100,000 hours and hours, infinite hours of music, digital music. So what advantage we have? One advantage is, yes, it is compressed. You can store a lot of information here. That's one information. So we have learned that how we can compress it, how we can optimally store it. Instead of 60 minutes, you have multiple hours. The second major advantage, how about sound quality? How about sound quality? So here we see that once we convert into digital, there is a compromise. But we listen to MP3 music, high quality, hi-fi, beautiful. And that C60, well, your father or grandfather's C60 cassette, if it still works, you play it on, I don't know, some Mehdi Hassan saying something, trying to say something, and sounds weird. What happened? The problem is that continuous time signal was a physical signal, and once we used to store it, the mechanism we had was magnetic tapes and all that. That magnetic tape physically rubbed with your recording head and reading head. So that cassette, that hi-fi, high sounding thing was good enough for initial maybe 10, 15, maybe 20 runs. After that, quality used to go down exponentially. And after about 1 month playing for, let's say 100 times, 200 times, it was all rubbish, garbage. And after 1 year, gone, almost gone. That was because of physical rubbing. Even if you don't use it that much, the age deterioration was also there. So that signal deteriorated. Now, although once it was recorded, it was almost 100%. But recording head and all that also compromised from 100% to, let's say, 99.5%. But still 99.5% was good. But after a few, let's say, times of playing, it went radically down 80%, 70%, 60%, 40%, and then all gibberish. If you convert from continuous into digital, okay, we have all that optimization techniques now from 100% to, let's say, 99.2%. So instead of 99.5, 99.2. But that digital conversion now is permanent, because it is not a physical signal now. It is not stored on some magnetic media. It is a set of numbers. And these set of numbers can be stored anywhere. And these numbers are not going to change. You play it 100,000 times, as many times as you want. As long as those numbers don't get changed, the quality remains the same. Get it? So this is the main reason that we convert a continuous time signals into a discrete time, into a digital signal, because that way it is secured now. It's not going to change, whether it is data for temperature, data for voltage, data for audio, whatever. Once we convert into this digital thing, it is a set of numbers stored on computer. They're not going to change. And we secure that, and we humans have also learned how to compress it and how to optimize it, and now in a very small USB or, I don't know, SD card, we can have gigabytes of data now. So this is main reason that why we discretize. Now this word discretize and digitalize is used synonymously. You should know the difference. Difference is very small. It is just how we represent it with a binary number or with a decimal number. Rest everything remains the same. Last question is the image discrete or continuous signal? I always get the same answer. Last so many years, you all belong to digital age. And that is why I keep getting that answer. You see, all
Discrete is.
all. Yes, I'm also getting the same answer discrete from this class here also. So online you are also answering me the same discrete. I get the same answer that it is a discrete signal. No, it's a continuous signal. You see, if you just imagine that right in front of you there is a square frame, empty frame. People who are seeing through that frame, you guys are sitting here, if I just hold an empty frame and through it you're seeing me. That frame is sort of an image. It's continuous. Why it is continuous? You take any point from x-axis and y-axis, X axis can be 2.184, Y can be 3, and it will have an intensity value, right? But why you guys belonging to digital age say that it is discrete or digital? The reason you say it as that, you are used to that megapixel. SLR cameras, all the image rays are concentrated in a small area, and this small area has a sensor which has packed 1 million sensors in that small area. So 1 million sensors means 1 megapixel. Now we have 10 megapixel, we have 100 megapixels stored and packed together in that small area. So that whole image is pixelated now, and at specific points only that thing is picked up. But because they are so closely packed together that your eyes cannot judge, so you feel that it's almost continuous. It looks continuous. It's not continuous. It is discrete. So this digital image is discrete or digital in nature, but in real world, image is continuous. There is not supposed to be any gap in between the pixels, whether it is 1 micron or 0.1 micron. There is no gap in between the pixel in real world. But in digital world, there is a difference. So image is continuous. But I will just quickly just show you. This is image. You see, but you guys belong to digital age because this image is projected through a SLR camera or something on a sensor which has all these pixels located where they are picking up the intensity value. Now once they are picking up intensity value from specific points, it has become discrete or digital now. And those values of intensity are stored as set of numbers. That image is stored as set of numbers. So we have this discrete or digital image. So this is all from my side. Questions? So we'll continue next time.